Question 9.1, the idea of a significance test, day 2. And we'll start by jumping right into an example. Calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health, the NIH, recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium on average. We want to write the hypotheses for the significance test. So our null hypothesis is that everything is normal. The teens are getting enough calcium, so we would start with mu equals 1,300. And the alternative will have some kind of sign that's not an equal sign, less than, greater than, or not equal to. And we're going to get that from the wording in the problem. It's noting that they are concerned they aren't getting enough calcium, which would mean that their mean calcium intake is less than 1,300. Remember that when we write these hypotheses, we're always writing them about a population parameter, mu or a p, never an x bar or a p hat. And then also remember that these two numbers will always be the same value. So we have our hypotheses here. Mu is representing the mean daily calcium intake in the population of all US teenagers. And then they're going to take a sample. So they have a random sample of 20 teens. They record their food and drink consumption for 1 day. And then the researchers use this information to find an average, which is 1198, and a standard deviation 411 milligrams. They perform a significance test and get a p-value of 0.1405. So we want to explain why there is some evidence for the alternative hypothesis, and we want to interpret this p-value. Now, the reason that there's some evidence for this alternative hypothesis is a logical one. In our sample of 20 students, they had an average of 1,198 milligrams of calcium, and that's less than 1,300. So there's at least some evidence that teens aren't getting enough calcium, but is it convincing evidence that the whole population of US teens is not getting 1,300 milligrams? And that's where the p-value comes in. When we look at a p-value, we want to see an unlikely result, something that's less than 5%. When we see something that has a probability of less than 5%, it's giving us evidence against that null hypothesis and in favor of the alternative. In this case, the p-value was 0.1405 or 14.05%. That's not unlikely. So in other words, if the teens actually are getting enough calcium, they're consuming 1,300 milligrams per day or more, just from the fact that samples vary, right? They're not always going to get the exact same amount. Sometimes they'll get a little more than 1,300, sometimes they'll get a little less. Our sample result of 1198 will happen about 14% of the time in a distribution where they actually are getting enough calcium. That's not unlikely, it's not unusual. We would expect this to happen fairly regularly. This is about a 1 in 7 chance. And because it would happen fairly regularly, we would attribute it to just natural sampling variation. So when it comes to interpreting the p-value, we always start off by saying if the null hypothesis is true, because we're basing this probability on a normal curve where that null hypothesis value is in the center. So assuming the mean daily calcium intake in the teen population is actually that 1,300 milligrams, there's a 14.05% chance or 0.1405 probability of getting a sample mean of 1198 or less. We say or less because we find the value from there shaded out to the end. And there's a chance of that happening by chance alone in a random sample of 20 teens. The final step in performing a significance test is to make a decision about the alternative hypothesis. And we're going to make that based on the strength of the evidence that we have. And that evidence is summed up in that single number, the p-value. If we have a small p-value, that's giving evidence in favor of the alternative hypothesis and against that null hypothesis. And that's because the results of our sample would be unlikely to occur when the null hypothesis is true. If we're seeing a result that has a p-value of less than 5%, that's unlikely. And it's unlikely, at least in our decision, because our initial assumption is probably incorrect. The null hypothesis is probably not true, and that's the explanation for why something looks unlikely. Large p-values, on the other hand, but when we say large, we mean anything above 5%. They fail to give us convincing evidence in support of that alternative hypothesis, and that's because these results are somewhat likely to occur in a distribution where that null hypothesis is true. So to summarize, if a p-value is small, we're going to use that to reject the null hypothesis and throw it away and conclude that there is convincing evidence for the alternative hypothesis. If the p-value is not small, if it's not less than 5%, we're going to fail to reject the null hypothesis and conclude that there's not convincing evidence in support of that alternative hypothesis. And we're going to write these answers in context, meaning that we'll write them about whatever the problem is about. How small does the p-value have to be? I've mentioned this many times at this point. Anything less than 5% is considered small, although we can adjust that range problem to problem. Now, looking back at that example that we did in day 1 of the notes, we had a free throw shooter who shot 50 free throws. He made 32 of them for a sample statistic of 64%. We run a test on this using a normal distribution where the null hypothesis is true. So when we look at that normal distribution, we see 80% is right in the middle. He's claiming he can make 80%, and all of these dots in this dot plot are simulated for a player who can actually make 80%. The results of this sample would be very unlikely. They're way in the tail of our curve. They're almost at a point where they're not even replicated. The lowest value we got looks like 62%, and he got 64%. So this is a very small p-value. The probability of this is 3 out of 400, which is 0.0075. That's less than 5%, and because this p-value is small, we're going to consider this strong evidence against that null hypothesis, and we're going to reject the null hypothesis. So to explain differently, based on how poorly he's done, we are rejecting his suggestion that he can make 80% of his shots. If that was true, he wouldn't have only made 32 out of 50. When we reject the null hypothesis, we're left with the alternative. And the alternative had said that he makes less than 80% of his shots. That seems very likely based on that sample statistic. So we have convincing evidence that the player makes fewer than 80% of his free throws in the long run. Now, the wording of a significance test seems a little weird at first. We're rejecting or failing to reject a null hypothesis, but it's consistent with what we see in jury trials here in the United States. We always start off with a null hypothesis that a defendant is innocent. The alternative to that would be guilty. And when we get to the end of a trial, we have one of two verdicts. We either find them guilty, in which case there was enough evidence to reject the assumption of innocence and conclude that they were guilty. If we don't have enough evidence, we don't find them innocent. We never say this null hypothesis is true. Instead, we just say that they're not guilty. This is where we're failing to reject that null hypothesis. A not guilty verdict doesn't mean the subject is innocent. It just means there wasn't enough evidence to convince a jury beyond a reasonable doubt. So when we fail to reject a null hypothesis, that doesn't mean our null hypothesis is true. It just means we don't have enough evidence to prove that it's false. So back to that calcium example, we had a p-value of 0.1405. What conclusion would we make? Well, this p-value is not small. It's not less than 5%. So we fail to reject the null hypothesis. We don't have convincing evidence that teens are getting fewer than 1,300 milligrams of calcium per day on average. So because this isn't small enough to reject that null hypothesis, all right, this average would happen somewhat likely. It's somewhat likely to occur in a distribution that's centered around that true mean of 1,300. And because it's not unlikely enough, we say that we don't have enough information to reject that 1,300. And because of that, we don't have enough evidence in favor of that alternative hypothesis. Now, to reiterate, this does not mean that the null hypothesis is true. We need to make sure that we're not saying any kind of conclusion that's stating that teens are getting 1,300 milligrams of calcium per day. That's not what our test is telling us. It's just telling us that we don't have enough information to prove that this value is incorrect. In the sample, I believe the sample result was 1198. That is a bit less than 1,300, so it's possible that they are getting less than 1,300 milligrams, but we need more data to actually conclude that. So with that said, we never want to use phrasing like we're going to accept the null hypothesis or the null hypothesis is true. That's never okay to write for a significance test. That will always be incorrect. If we were to actually make a confidence interval for this data, we would find a range from 1039 to 1356. Remember that any of the values in that range are plausible for the true mean amount of calcium that teenagers get. And this is just one value. It could be 1300, but it could be below it or above it.